How's it going, folks? So this video is for my Algebra 3-4 students or anyone who wants a little bit of a refresher on the basics of trigonometry. So when I say trigonometry, you might be thinking about triangles. So back in geometry, you learned this basic idea with trigonometry that we can use the trigonometric ratios like sine, cosine, and tangent to measure the sides of a circle or the angles within a circle. And that's what your assignment is going to be predominantly on this week, so you get a refresher of those basics. But in this class, we're mostly focused on the graph of these functions. So if I graph sine of x, you're going to see something like this. You're going to see a wave. So these trig functions give us these sinusoidal waves. Cosine looks pretty similar. We get this wave function. Now, there are tons and tons of really cool applications where we can use our knowledge of how waves behave to understand things in our world. It doesn't take a huge imagination to think about all the things in our world that are represented with waves. If we think about light comes to us as a wave, or anything on the electromagnetic spectrum, from the visible light we have to microwave and radio waves, X-rays, all those kinds of things come in the form of a wave. Pretty much anything that you can see or hear is arriving to your ears and your eyes as a wave. So understanding those waves can tell us a lot about the world around us. A cool example of that is music. So when we play a note, what we're hearing is actually a wave function, right? That vibration back and forth. And that vibration, that wave, is going to change depending on the note. So if we go higher, we see the wave, the frequency speed up. And as we go lower, it really slows down. Barely hear that one. That one's a little outside of our hearing. So whether it's the things we can see or the things we can hear, all these things are represented by wave functions. Now, one quick note here. When a person sings or a musical instrument is played, we don't actually have this perfect wave function like digital instruments give us. There's a lot more variation that goes on. This is the basic outline of that note. Cool. So not only can sine functions help us represent literal waves, but anything in our world that vibrates or repeats or has any sort of pattern. So imagine you are an engineer and you're building a skyscraper. Sometimes skyscrapers shake a little bit. If there's really heavy winds or an earthquake, like in this GIF here, is an earthquake in Japan, we see two skyscrapers vibrating back and forth a little bit. So engineers consider this possibility, and they want to make sure that their building can handle that sort of back and forth stress, which can be represented with a sine wave. Another really great example is the Tacoma Bridge up in Washington, which had some pretty gnarly vibrations going through it, and ultimately this thing collapsed. Not only things that are vibrating, but anything that sort of repeats can be represented with a sine wave. So here we see the tide, right? The tide comes up and down, back and forth in a really predictable way. You can represent the height of the ocean on this beach with a sine function. So you might be thinking, how the heck do we get from those triangles that we learned back in geometry to this sine wave? So the way we do that is through the unit circle. So I'm going to try to explain here, how do we go from this simple idea of SOHCAHTOA to a sine wave. Okay, so imagine you have a unit circle. So by unit circle, I mean it's a circle and its radius is 1 unit. So we go out 1 to get to the edge in any direction, right? A circle is equidistant from the center on all around the side. So it doesn't matter if you go straight to the right or up or at an angle like this. But if we do go out at an angle, so again, the way out to this point, if we go directly there, the radius of this circle is 1. So that length is 1. Well, what if we wanted to represent where this point is? So typically when we look at a graph, we can represent where the point is with an x and a y. So we have an x representing the horizontal distance. How far do we have to go left or right to get to that point? And then we have the y value, which represents the vertical distance. How far up or down do we need to go? So we can represent this point in space using a horizontal distance and a y distance. So hopefully you're starting to see the connection here. What we've just built is a right triangle. So with this right triangle, we already know one of the sides, because I just said we're dealing with a unit circle. So our hypotenuse is a radius of that circle, so it's 1. So if I know my basics, if I know SOHCAHTOA, so sine is the opposite side over the hypotenuse and so on, then I can figure out how far is x and how far is y if I know an angle. So let's say that this angle is 30 degrees. This is very hard to write with. All right, so let's say that angle is 30 degrees. Can we figure out how far did we go out in the x direction, or how far did we go up in the y direction? So let's start with y. So how far is this distance? How far do we have to go from the x-axis here to get up there? So we can figure that out using trigonometry. So I'm dealing with the opposite side and the hypotenuse, since I already know the hypotenuse is 1. So if I need opposite and hypotenuse, remember SOHCAHTOA, opposite hypotenuse is going to be so. So we're using the sine function. So I can do sine of my angle, in this case that's 30 degrees, is going to be equal to the opposite side, so y, over the hypotenuse, which we know is 1. Cool. So we're going to get to the point where we have some stuff like this memorized, but for now let's take a look at the calculator. So I'm going to do sine of 30 degrees. There are a couple different ways to measure angles. You can measure in degrees or something called radians, which we'll talk about in this class, but you want to make sure your calculator is set up correctly. So you hit the mode button, and then you'll see a setting here where you can change from radians to degrees. By default, your calculator is usually set to degrees or radians mode. So you want to change it since we're talking about degrees here. Cool. So after I change my calculator settings, I go sine of 30 degrees, and we're going to see that's 1/2 or 0.5. So the y-coordinate is 1/2. That's how far up we have to go to get to this point. We can do something really similar for the x direction. So to figure out how far are we going in the x direction. So if we go back to SOHCAHTOA, this time we're dealing with the adjacent side. So adjacent just means next to. So this red side here is adjacent to the angle. It's right next to it. So we got the adjacent side is what we're dealing with, and the hypotenuse, which means we're using cosine. Cosine represents the ratio of the adjacent over hypotenuse. So for the red side, we need to use cosine of the same angle, 30 degrees. All right, that's equal to the x direction, which we don't know yet, over the hypotenuse, which is still 1. Cool, we can throw that into our calculator, and it'll tell us that's about 0.866, okay? So the cosine is about 0.866 or so. We're going to talk about a different way to represent that same value, and that is the square root of 3 divided by 2. Later on, we'll learn that this is a very special triangle, and those are the same value. But 0.866 is fine. So this side is equal to the square root of 3 divided by 2. So this point in space can be represented by root 3 over 2, or 0.86, and 1/2. So this is how we get from our basic triangle SOHCAHTOA to a sine wave. So I really like this animation here. Hopefully this is showing up well with the frame rate of my video capture here. But if we think about sine, as we saw in our circle, sine represented the y direction. So how high up on the circle we are. So the sine graph is following the vertical height of that point on the circle. So if you notice, this is sort of tracing, right, that just the height around the circle. Meanwhile, cosine is doing the same thing for the x value. So we go left, we're all the way down. As we move to the right, the cosine is shooting up. So that's the connection between that basic triangle trigonometry you learned in geometry and the big picture of what we're going to be doing here in advanced algebra. Thanks for watching, guys. Good luck with your assignments, and there's more to come next week.